Namaste and a very good afternoon to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a deep learning model using Keras to predict the housing price for Boston housing dataset. Even before I proceed to demonstrate how to build a deep learning model using Python, may I request you to subscribe to my channel, also like and share my videos. Let me begin by drawing your attention to the data set that I'm using. This is a very popular data set. It's called as Boston housing data set. You can get this data set from Kaggle. There are a lot of details about the characteristics of the towns in Boston. Some of the variables here are crime rate, ZN, Indus, presence of Charles River. Next, you have a variable called as nitrogen oxide. RM stands for the number of rooms, the average number of rooms. Then you have age, distance, the variable radius. I'll explain each of these variables in detail in a few moments from now. You also have other variables like PT ratio or pupil to teacher ratio, the number of colored people living in a town, the percentage of lower status of people living in the town. Last but not the least, we have median value of the housing prices. You can see here, this is a very important variable because we'll be using this particular variable as the dependent variable. So median value of the housing price is what we are interested in predicting. What is so interesting about this? The interesting facet about this particular variable is that it is a scale variable, and we will be building a deep learning model to predict a scale dependent variable. I repeat, we will be building a deep learning model in Python to predict the median value of housing prices in Boston. What is the sample size in this particular data set? When I scroll to the last record, in fact, let me just select this entire column. You can see here, the count is 506, which means that we have a sample of 506 records to build a deep learning model. Let me interpret some of the important characteristics of the first locality. In the first row, we are talking about a locality which has approximately 1% crime rate. Then we have 54% nitrogen oxide concentration. Nitrogen oxide concentration is used as a determinant to gauge or assess the level of pollution. Next, we have the average room size. So if the number of rooms are higher, it automatically means that we are talking about a large house. Then we have age. Interestingly, we have other important variables like PT ratio, blacks, LStat, LStat, and last but not the least, the target variable. We would like to use each of these 13 variables as the independent variables to predict the housing price of Boston. With this background, may I now take you to Python, wherein we will be running a few codes to see how a deep learning model can be built in Python. Right now, I am in Jupyter Notebook. This is the interface of Python. As you can see here, we are going to build a deep learning model on the Boston housing dataset. What is the goal behind this project? The goal behind this project is to build a model that can predict the median value of owner-occupied homes in thousands of dollars. Let me repeat this for you. We are going to build a model. What kind of a model? A deep learning model that can predict the median value of owner-occupied homes in thousands of dollars. Now, let's look at the first snippet of code. In the first snippet of code, what I'm doing is I'm importing the necessary libraries. I'm importing NumPy package. Similarly, I'm also importing the pandas library. NumPy is a package which supports mathematical operations, and pandas is a library which facilitates data munging and data wrangling. I would need a data set to play with, and therefore I will be loading the Boston file from sklearn.datasets. What is sklearn? sklearn is a machine learning library which has many different functionalities that can be used to run a machine learning model. There are a lot of data sets that comes in pre-built into this particular library. One of the data sets is Boston, and we will be using the load_Boston function from sklearn.datasets to load the file. Now, let me make a move on to the fourth line of code. As you can clearly see here, I am importing the train_test_split function from sklearn.model selection. As the name itself suggests, what we are trying to do with this particular function is to split the data set into two parts. The first part is called as the training data set, and the second part is called as the test data set. Typically, 70% of the records will be pushed into the training data set, and these 70% of the records will be again fed into the deep learning model. The deep learning model will learn the characteristics from the data and give you the results. Those results are applied on the test data. And once we get the predictions on the test data, we will be comparing the actual versus the predicted to assess the overall quality of the model. So long story short, what we are doing with this particular functionality is to simply split the data set into two parts. We also have another important functionality, standard scalar. We will be importing this particular functionality from sklearn.preprocessing. This is done to standardize the variables. Many times we'll observe that there are two different variables which are measured in two different units. It becomes a bit difficult to run a deep learning model when you have variables. Let us say one is expressed in centimeters and the other one is expressed in weights. The general tendency of any mathematical model is to give higher weightage to those variables which have large values as compared to a weightage to a variable with smaller values. So since larger values tend to swarm or dominate the smaller values, it's always good to standardize the variables, which is part of the data pre-processing stage before feeding the data into deep learning model. Now we have the hero of this particular analysis, TensorFlow. TensorFlow is a very, very high-level API that was provided by Google. TensorFlow is used widely to build deep learning models. What am I doing next? I am importing the Keras library from TensorFlow. Lastly, I'm importing layers from TensorFlow.keras. So the overall theme of this particular snippet of code is to import the necessary libraries which will support us in building the deep learning model. Once we are through with importing the necessary libraries, the next thing will be to load the Boston housing dataset. Now, this is an important step. As you can see here, in the third statement of the earlier code, I've used load_Boston. In the second line, in the second snippet of code, I'm using the load_Boston and saving it as an object called as Boston. So when I execute this particular command, the Boston file will be loaded. Now, what are the important feature names in Boston? You can use Boston.feature names. This is the method that we can use to display the feature names. You've already seen some of these features in the spreadsheet. Let me again run through some of the important variables: crime rate in a locality, nitrogen oxide concentration, number of rooms, then you have pupil to teacher ratio, the number of colored people, then you have lower status of population, which will be used as input variables to train the deep learning model. Let me now scroll down. If you want a clear description of this particular data set, you can run a print of Boston.description command. When I go ahead and execute this particular command, what you observe is this gives a detailed description of the data set. Let's look at this particular data set, Boston house prices data set. Number of instances is 506. When we say number of instances, we are referring to the number of records or the sample size in this particular data set. Number of attributes is 13. The median value is usually the target. Of course, we agree the median value of the housing price is what we will be using as the target. Let's quickly look at the description of some of the variables. The first one is crime. What does this indicate? This indicates the per capita crime rate by town. I repeat, this indicates the per capita crime rate by town. You have another interesting variable which is called as ZN. What does this indicate? This indicates the proportion of residential land zoned for lots over 25,000 square feet. So that is what we have as the second variable. The third variable here is the index variable. What do we mean by index? It's the proportion of non-retail business acres per town. I repeat, it's the proportion of non-retail business acres per town. The fourth variable is the CHAS variable, which stands for Charles River Dummy Variable. Next, we have NOx, which indicates nitric oxide's concentration expressed as parts per 10 million. Some of the other variables that we have would be average number of rooms per dwelling. The variable age is shown as a proportion of owner-occupied units built prior to 1940s. You have the variable distance. What does this indicate? Weighted distances to 5 Boston employment centers. Next, we have the variable RAD, index of accessibility to radial highways. We have the variable tax, PT ratio, and B, or the proportion of black people by town. LSTAT represents the percentage of lower status of population. And lastly, what we have is the median value of owner-occupied homes in dollar thousands. Now, this data set is largely because of the contribution of two of the creators, namely Harrison and Rubenfeld. Let me scroll down. We'd like to take a look at the data set. Let's just get a high-level perspective of this data set. What we are going to do is we're going to use pd.dataframe. I repeat, pd.dataframe command on the boston.data file. We can also look at the different columns that are present in. We'll be also displaying the column names, which will be obtained from boston.feature names. Let's go ahead and execute this particular code. You can see here, when we type boston_df.headoff, we'll be getting the first 5 records, the first 5 rows of the entire data set. Now, most of you who are new to Python may be wondering as to what is a data frame. Data frame is an option that is present in Pandas. It simply gives a spreadsheet-like view. You can see here, we are getting a clear spreadsheet-like view when we convert any object to a data frame. Next, very curiously, in the earlier data frame that we used, we had a list of independent variables. But what was missing from the data set was the dependent variable. What we are doing at this stage is we are going to use boston.target, and we're going to create a new variable called as medv, which is going to give us the median value of the housing price. Now, at this stage, what I'll be doing is I will be showing you a bit of EDA, or exploratory data analysis. Now, instead of using 14 variables and constructing a correlation matrix, which will be a giant matrix with 14 variables along the rows and 14 variables along the column, what I've done is, just for the sake of display, I have filtered only the top 6 variables. So these are the top 6 variables that I have, which I will be using for further analysis. You can see here, crime rate, NOx, number of rooms, the number of blacks, LSTAT, and median value of housing price. I've used a simple command which is called as the dot loc function. Boston underscore df is the name of the data frame. Then I can use the dot loc function. Typically, this is a good interview question wherein people ask what is the difference between dot loc function and dot iloc function. You can either use the dot loc function or the dot iloc function. When we are using the dot loc function, we have to explicitly state the variable names here. I am subsetting the variable names. I'm using this as a list and creating a new object which is called as Boston underscore df1. Let me go ahead and execute this particular command. Let me display what do we have in Boston underscore df1 dot head of. Let me scroll down. You can clearly see here there are only 6 variables that we will be using. I like to run a correlation matrix with these 6 variables and look at the EDA or exploratory data analysis from a high-level perspective. You can see here, I'm using the .core of method. On the entire data set, I can simply run .core of function and save the results of the correlation matrix as X. Let me now go ahead and run this particular command. You can see the output of this particular code. What you're seeing here would be a 6x6 matrix wherein you have the correlation values. Correlation is a good foundation for any model, especially when you have a scale-dependent variable. Remember, the correlation has a range between -1 and +1. I repeat, correlation has a range from -1 to +1. The correlation value cannot be greater than +1. Correlation value also cannot be less than -1. If the correlation is exactly +1, it means that there's a perfect positive relationship between the variables. On the other hand, if the correlation is exactly -1, it means that there's a perfect negative relationship between the variables. Thirdly, if the correlation is exactly 0, it means that there is no relationship between the 2 variables. Typically, if the correlation value is greater than 0.7, we say that there is a strong relationship between the 2 variables. If the correlation value is less than -0.7, we can state that there is a strong negative relationship between the variables. I like to draw your attention to one number here, -0.38. What does this indicate? Please observe the column here. This is median value of housing price. Let's observe the crime rate here as the row. This means that the correlation between crime rate and median value of housing price is -0.38. There is a negative correlation between crime rate and housing price. However, it is not a strong relationship. Why do I say it's not a strong relationship? Because the correlation value is not less than -0.7. We can interpret the rest of the numbers the same way. But as you can see here, because we have so many numbers, interpretation of this correlation matrix becomes very difficult. Is there an easier way of interpreting this correlation matrix? The answer is yes. There is an easier way of interpreting this particular correlation matrix. How do we interpret this particular correlation matrix? The answer to this question would be a heat map. You can use a heat map and color code each and every number here. And based on the color, you can make important inferences based on the correlation. Let me now proceed to show you how to create a heat map in Python. This is the code that I'm running. Import Seaborn as SNS. Seaborn is the library which has the heat map function. I'm giving SNS as the alias name for Seaborn. We can type sns.heatmap. The first parameter that we are feeding here is X. CMap represents the color coding. Red, RD stands for red. YL stands for yellow and GN for green. We have red, yellow, green. These are the 3 different colors which we will be using to color code the correlation values. And the last of the parameter values that I'm specifying for is annotation equals true. Let me go ahead and execute this particular command. You can see here, we are getting a heat map. This is the output of the heat map that we are seeing. You have different variables like crime rate, nitrogen oxide, rooms, the proportion of blacks, lower status of population, median value. The same variables are repeated along the column as well. Since median value of homes is the target variable, let us focus on the last row and what is the behavior of each of the independent variable with that of the dependent variable, namely median value. How are the independent variables related to the dependent variable? That is the question. Let's now look at the color coding. What Seaborn package has done is it is telling you what the colors represent. Remember, I told you that correlation lies from +1 all the way to -1. Darker the red color, darker the shade of the red color, it implies that stronger is the negative relationship. Darker the shade of the green color, it implies that the correlation is strong and positive. You can also see a few yellow colored cells indicating that the correlation is quite moderate here. So there are three situations. Wherever you see dark red colors, it means that the correlation is strong and it is a negative correlation. Wherever you see dark green color cells, it means that there's a strong positive correlation. And wherever you see yellow colored cells, it means that there's a moderate relationship between the variables. Let me now draw your attention to these 6 cells. Why specifically these 6 cells? Simply because this indicates the relationship with the target variable, namely median value of housing price. I like to draw your attention to this number. Look at the shading of red. It is dark red. The value is quite high, -0.74. It is greater than -0.7. So since this value is quite strong, if you look at the absolute value, it is 0.7 exceeding 0.7, which means that there is a strong negative relationship between percentage of lower status of population and median value of the housing price. Therefore, heat map has used dark red color to indicate this relationship. What is the business implication? The business implication is in any town or in any locality, if the percentage of lower status of population goes up, the median value of housing price comes down. So there's an inverse relationship between median value of housing price and lower status of population. So if you want a locality wherein there is a high value for median value of housing price, perhaps you will have to live in areas wherein there is a high percentage of lower status of population. While this is in dark red, let me also draw your attention to another cell which is dark green. You can observe here, this is 0.7. Rooms, RM here represents rooms, has a strong positive correlation with median value of housing price. What does this indicate? This simply indicates that as the number of rooms in a house increases, the median value of housing price also increases. So there is a positive relationship, which means that the room size increases, the median value of the housing price also increases. When you look at some of the other cells here, it is -0.39, -0.43. It indicates that there is a weak negative relationship between median value of housing price and crime rate. There's also a weak negative relationship between median value of housing price and nitrogen oxide. While looking at the last row is important because it tells us which variable has what kind of relationship with the dependent variable, it also might be worthwhile to spend time looking at the other cells, because this would indicate which of the variables would be related amongst the independent variables. I'll skip that portion and make a move on to the next snippet of code. Yes, this is an important step in the analysis. Why is this an important step? This is an important step because we are using train underscore test underscore split functionality to split the entire data set into training and test. 80% is used for training the data and the balance 20% is used for testing. One of the arguments that we are specifying here is Boston underscore DF. This is the source data which will be used to split the data. Next, we have the median value of the housing price, which is the dependent variable. The test size here is 20%, which automatically means that 80% will be used for training the data. Last but not the least, we have the random state value as 42. When you go ahead and execute this particular command, what you will be getting is a tuple. You will get x underscore train, x underscore test, y underscore train, y underscore test. You can use the training data sets to train the model. Similarly, you can use the testing data set to test the results of the model. So at this stage, we have created 4 new data sets, namely x underscore train, x underscore test, y underscore train, y underscore test. The next stage is to standardize the data. I repeat, this is the stage wherein we will be standardizing the data. As you can see here, we will be using the functionality standard scalar, saving it as an object called as scalar, and we will be using scalar.fit underscore transform. We'll be doing 2 tasks here, fitting as well as transformation on the independent variables. I'm feeding x underscore train as the input for fit underscore transform. I'll be saving the results in x underscore train. Next, we will be using scalar.transform on x underscore test and saving the results in x underscore test object. Let me go ahead and execute this particular command. So what we have done at this stage is standardization of the data. Standardization typically is used when you have variables which are measured in different units. Now, this is a very, very important step. After standardizing the data, we will be using not the raw data, but the standardized data to train a deep learning model. Even before we train the model, we have to specify the architecture of the model. We can look at the blueprint of the model. The command that we will be using is keras.sequential. What is the command? The command is keras.sequential. Let me just explain this code. The code is defining a neural network using the Keras API. This particular model has 4 layers. You can see here, this is the first layer. Then we have the second layer, followed by the third layer, and this is the final output layer that we have. Since this is important, I'd like to explain this step by step in a detailed fashion. What is happening in the first layer? In the first layer, what is happening is that we are using a fully connected dense layer. I repeat, we are using a fully connected dense layer with 64 neurons. Please observe this. We are using 64 neurons and a ReLU activation function. It takes an input shape of the training data. You can see here, we are feeding the input shape of the training data, x underscore train, with the number of features of input variables being x underscore train dot shape of 1. Since we have 13 columns as the input variables, the input shape here will be 13. We don't have to worry about it because this particular command will automatically fetch the number of features. That is as far as the first layer is concerned. Let's now focus on the next 2 layers. What is happening in the next 2 layers? The next 2 layers are also fully connected layers with 64 neurons and an activation function called as ReLU activation function. Last but not the least, we are using a dense layer. This final layer is a fully connected neural network with a single neuron. You can clearly see here, there is a single neuron that we are using, which is used for regression tasks. It does not have an activation function, which means that it will output a continuous value. Overall, the model has a total of 3 hidden layers. I repeat, at an overall level, the model has a total of 3 hidden layers with 64 neurons each and 1 output layer with a single neuron. It is commonly used for regression tasks, and the activation function used in the hidden layers is relu, which is known to work well for many types of problems. I hope this clarifies the architecture of the deep learning model. Once you have specified the architecture of the deep learning model, the next stage is to compile the model. Here, I'm going to use model.compile. The optimizer function that I'm using is the Adam optimization. The loss function that I'm using is mean square error, and the metrics that we will be using is mean absolute error. Let me go ahead and compile this particular model. After compiling, the next stage would be to train the model. How do you train the model? You have to run a simple command which is called as model.fit. Inside this model.fit, there are different objects that we are using. The first object would be the training data set, which has all the input variables. The second object that we will be using is the dependent variable from the training data set. The validation split here is 20%. Batch size is 32. We will be using 100 epochs in this particular training. Let me just jog your memory as far as the last 3 steps are concerned. What we are doing here is to build the deep learning model architecture. Prior to this, we have standardized. After standardizing, we are building the deep learning model. Once we have built the deep learning model, we are compiling the model. After compiling the model, the next stage is training the model. So this is a simple strategy that we can always use. Standardize the variables. After standardize, specify the architecture of the model. After specifying the architecture of the model, the next stage would be to compile the model. And the 4th stage would be to train the model. Let me now look at the final results of the model. If we go ahead and execute this particular command, you are getting very important steps here. What you are able to see is the loss function is 11.65. The mean absolute error value is 2.2159. You are shown 2 different statistics here. The first one is the mean square error value, and the second one is the mean absolute error value. Lower values of mean absolute error and mean square error are always preferred. If the mean absolute error is on the higher side, it means that the training is poor, and hence the model that you built is also poor. A value of mean absolute error, which is typically less than 5, is a good sign, and it indicates that the model fits the data well. With this, I have come to the end of today's video. In today's video, we have seen how to build a deep learning model on a scale-dependent variable. There are quite a few steps that we went through. We looked at important steps in feature engineering, like how to standardize the data. Then we also did exploratory data analysis. We constructed a correlation matrix, and using the SNS.heatmap, we were able to generate a heat map for the analysis. Further, we specified the architecture of the model, compiled the model, and trained the model using the model.fit command. With this, I have come to the end of today's video. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this particular video. Have a great day ahead.